Hello, and today we're going through binomial expansion for A-level maths, and let's get started. So first is to learn how to expand binomials. So say a binomial is when you have something like this, where you have A plus B to the power of something. So say we have to the power of 0, this is equal to 1. So if we increase the power, we'll have to the power of 1, which we can make, this will be written as 1A plus 1B, because we actually don't change anything in the expression because it's just to the power of 1. Now to the power of 2, a plus b to the power of 2, we would get 1a squared plus 2ab plus 1b squared. And now if we do this for a plus b to the power of 3, we would get, and if we do this one more time for a plus b to the 4, we would get, and let's see common trends we can get from this. So first of all, let's look at the coefficients. So as you can see, the coefficients seem to follow some sort of triangular shape, and this is what we call Pascal's triangle. We'll go into more detail later on. And also another thing you can see, so if we look at the last expression, we can see that the powers of a are decreasing, so you're dividing by a every time in each part of the sequence or the series of the binomial expansion. And then for each of them, you're also multiplying by b. So either a decreases or b increases. And then if you were to flip it, it's so going the opposite direction, starting from this side, ending this side, it will just be the other way around. So you'll increase a going backwards, and you'll decrease b going backwards as well. Now let's go on to Pascal's triangle. So before we said that the coefficients of the expansions of increasing powers of binomial expansions, we would get a Pascal's triangle. So how would we form a Pascal's triangle? Start with a 1 at the top and then 2 1s on the side, and we form like a small triangle. And now on below that, we would do 1s on the sides, and in between the two, we would just add up the 2 1s on top. So we'd get 1 plus 1, which is 2. And then we'll go down, we'll have a 1 on the side as well, and then we'll add this one, 1 and a 2, which will get 3, and we'll do that for this side and this side as well. We'll get 3, and then we'll put a 1 in the edge. And we can keep going, where we add the 1 and the 3 is a 4, 3 plus 3 is 6, 3 plus 1 is 4, and 1. And you can see this forms the exact same coefficients that we had before in our expansions. And we can keep going. Say each row corresponds to a power of the polynomial. So say we call that n. So that a plus b to the n is the expansion. This is where the coefficients follow each row of the triangle, where n equals 0 is the first row, n equals 1 is the second row, n equals 2 is the third, n equals 3 is the fourth, n equals 4 is the fifth, and n equals 5 is the sixth row. And then you can carry on doing by adding 1s on the sides and then adding the in-betweens to carry on doing the Pascal's triangle. So now let's try a quick expansion, knowing what we've just learned. So this is to the power of 5, as we can see. So we can do a Pascal's triangle up to the 5th, so we can get to the power of 5. And this would be to the power of n is equal to 5, which is what we need. And remember, we said that the powers would increase in one direction, one of the values of the binomial, and then for the powers would decrease in the same direction. So let's draw this out. So how we can write it would be 2a minus 3b to the power of 5 is equal to, and then we can write out all the coefficients in a column, so it's nice and easy. And now we can multiply them by increasing and decreasing powers of the 2 points, so 2a or minus 3b. We can start off with 2a to the power of 5 times the minus 3b to the power of 0. And then we'll go back up. So we'll decrease the power here, so we'll have 2a to the power of 4, 2a to the power of 3, 2a to the power of 2, 2a to the power of 1, and 2a to the power of 0. And then we can multiply to get second term, we will just increase the power, so minus 3b to the power of 1, minus 3b to the power of 2, minus 3b to the power of 3, minus 3b to the power of 4, and minus 3b to the power of 5. And now we have all the terms, and all we have to do is just add them up like this. And if we write it out, we would have, so for every term, I can just expand out the power times the coefficients and the a's and the b's. So we can do for the first one, we can get 2 to the power of 5, which is 32, a to the power of 5, and because it's to the power of 0, we can just leave this as 1. Then we would get minus 3 to the power of 1, so minus 3 times 5 times 2 to the power of 4, which is 16 times a to the power of 4 and b to the power of 1, which is b, and we should get minus 240 a to the power of 4b. And we keep doing this for each one, and we should get something like this. So now we have all the terms in our expansion. We can just write it out, and we would get, and this would be your final expression for the expansion of the binomial. If we were to do questions like this, just remember, find each term of the expansion, find out all the coefficients and the powers for each one, and then join them together to get the final expression. And remember, you can use Pascal's triangle. So if you can see in this previous question that we just did, that because we have one of the terms as negative, we're going to have a positive, then negative, positive, then negative, positive, then negative for all the terms of the expansion. If one term of the binomial is negative, the expressions will oscillate between positive and negative in the expansion. So say you have a minus b to the power of n, you would get positive for the first one, negative for the second term, positive again, then negative, and then positive, and it will alternate for the whole series. So now let's move on to the constant term of a binomial expansion. So the constant term is just the term with x to the 0, and this will also have a coefficient in front. Now let's go over the choose function, which is a really useful function to find the coefficients of the expansion. It's very similar to finding a Pascal's triangle that is really big and finding each term for the Pascal's triangle. So for example, this is the choose function. It's called, you write it as NCR, which can be written as this sort of vector form as well, but it's not actually a vector, it's just a function. And this function is made by doing n factorial times r factorial, so the inputs would be n and r, and the output would be this whole expression here. Just a bunch of factorials multiplied and divided by each other. In this case, it's good to know that if you put a 0 in any of the terms, that 0 factorial is equal to 1. And there's a few rules that you could know about this. So n choose r would be the same as doing n choose n minus r. It would be the same value of an outcome that you would get. And then n choose 0 is always 1, and n choose 1 is always n. And n choose n, because of the fact that n choose r is the same as n choose n minus r, so n choose n would be the same as n choose 0, which is 1. And then we can also form Pascal's triangle using the choose function. So 0 choose 0, if we were to write it down, 0 choose 0 is the same as 1. And 1 choose 0 is also 1 because of this fact here. And then 1 choose 1 is also 1. And if you carry on doing this, it looks like a Pascal's triangle. So here we have a Pascal's triangle where the n choose r. We've used n choose r to create the Pascal's triangle, where n is the row, or they remember in a binomial, a plus b to the power of n. So it would be the power of the binomial that we're trying to expand. And the value of r is the term in the series. Say you have an expansion of this plus this plus this plus this plus this. R starts at 0, r becomes 1, r equals 2, r equals 3, and then for the expansion it just keeps going for the number of terms. So the r is the number of terms and n is the power of your expansion. And you can create the coefficients of your binomial expansion using the choose function, using the fact that you know what n is and you know what r is. Now let's try an example where they ask us to expand the first four terms in the binomial 1 minus 3x to the power of 7, where the x power increases per term. So in this case, instead of drawing Pascal's triangle, we can just use the choose function. So we know that our n is equal to 7, and we know that our r's is going to start from 0 all the way to the final term. So our coefficients would be, so say we do the same as before, we expand it out like this, equals, so we would do, instead of the coefficient, we would do 7, choose 0, 7, choose 1, 7, choose 2, 7, choose 3, 7, but we're going to leave it up till 3 because they're asking for the first four terms of increasing powers of x. So, and now we multiply this by increasing powers of x, so we would also have increasing powers of minus 3x. So multiply by minus 3x to the power of 0, minus 3x to the power of 1, minus 3x to the power of 2, and minus 3x to the power of 3. And then we will have to multiply this by decreasing powers of 1, so 1 to the power of 7, 1 to the power of 6, 1 to the power of 5, and 1 to the power of 4. Because if we were to carry on the expression, we would go all the way to x to the power of 7, minus 3x to the power of 7, or 1 to the power of 0, because it's the n is 7, so it's the maximum power we can go to. Now this is equal to, each term is equal to, and remember we have to add them up for the expansion. We would get, so 1 for the first term, because 3x to minus 3x to the power of 0 is just 0, it's just 1, because anything to the power of 0 is 1. We get minus 21x plus 189x squared minus 945x to the x cubed. So if we write this out, we would get 1 minus 21x plus 189x squared minus 945x cubed. And these are just the first four terms of the expansion of the question. Now let's move on to expansion using the choose function formula. So we're going to generalize this now as a formula. So if we want to expand something like this, a plus b to the power of n, we know that we're going to get n choose 0 times a to the n times b to the 0, which is just 1, plus n choose 1, a to the n minus 1, times b, plus n choose 2, a to the n minus 2, b squared, and so on. So we can write this out as a general formula as a plus b to the power of n is equal to the sum of terms from r equals 0 to r equals n. And each term will look like this: ncr for increasing values of r from r0 all the way to rn, and a to the power of n minus r, and also b to the power of r. And this would be a general formula for the binomial expansion. So now it's nice and condensed, and it will be easier to remember and understand, so you can apply it to future questions. So now let's move on to this question here, where they ask to expand the binomial x plus 1 over x to the power of 10 and find the coefficient of x squared in the expansion. So we don't have to expand the whole binomial, we're just going to have to find the coefficient of x squared in this expansion. So we have two components of the binomial, the x and 1 over x. So x would have to be the power of a value a, and the 1 over x would have to be to the power of a value b, which is equal to, which will get us a coefficient of x squared. And we can write this out as x to the a times x to the minus b is equal to x to the 2. So the coefficients have to be two numbers you can take away, a minus b is equal to 2 because of exponential rules from the x powers. And also remember they have to add up to make 10, which is the total power of the binomial. So a plus b have to equal to 10. So now let's find the values of a and b. So what we can do is we can add both equations and we would get 2a is equal to 12, and minus b and plus b cancel out. So we'll get a is equal to 6. And if we take away both equations, so we would get the a minus the a, which is just gets 0. And then we'll have the minus b minus the plus b, which will get minus 2b, is equal to 2 minus 10, which will get minus 8, which we can divide by minus 2 on both sides. We'll get b is equal to 4. So the powers of the terms would be x to the power of 6 times 1 over x to the power of 4. Or you could have substituted a into any of these equations to find what b was instead of doing this long step. And to find the coefficient, you can just do n, choose either 6 or 4, but you would get the same answer, so it wouldn't matter if you use 6 or 4. And 10 choose 6 or 4 times this whole expression would become x to the 6, 1 over x to the 4, which is x to the 2. So we get 10 to the 6, x to the 2. So the coefficient would be 10 choose 6, which is equal to 210. So this is the coefficient, and that's the answer to the question. It is also worth knowing that the sum of the powers, a plus b, in the expansion is always equal to n. So for any term in the expansion. Now let's move on to the expansion of 2 to the power of n. And this is very simple. So say we have a binomial, a plus b to the power of n. We know that this would be expanded as nc0 times a to the power of n times b to the power of 0, then n choose 1, a to the power of n minus 1, b 1 plus n choose 2, a n minus 2, b2 plus etc. So to find 2 to the n as an expansion, we can actually write this out as, if we make our a is equal to 1 and our b is equal to 1, we can get 1 plus 1 to the power of n is equal to 2n, which we can expand as well, which is n choose 0 times 1 to the power of n and 1 to the 0, and then which these two will become 1, so we can just cancel them out. Then we'll get n choose 1, then 1 times n minus 1 times 1 to the power of 1, which this whole expression will be 1, so we can cancel the multiplication as well. We would cancel all the multiplications because they will all be 1, and we will just get an expansion like this, and choose 3 plus etc. like that. And this would be the expansion for 2n. So if they ask any particular power of 2, you can just do, for example, 2 to the power of 2, you'll get 2 choose 0, 2 choose 1, plus 2 choose 2. And then it will just go up to n, so you can't have 2 choose 3 because that would not be a possible value. So we just have up to all the values that until r is equal to n. Now let's move on to percentage error. So the formula for percentage error is just this. So it's the percentage error is equal to the actual value minus the approximation all over the actual value times 100 to get a percentage. And this is the modular sign, which makes everything positive. And this is very useful when they ask you to expand a binomial to a certain amount of terms. So you would compare the actual value to an approximation using an expansion of a certain amount of terms, so not all of them. So you can find the percentage error of your expansion. Now let's move on to the final bit, which is a question to apply the percentage error. So part A would be to find the expansion of 1 minus x to the power of 4, 1 minus x to the power of 4, is equal to 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3 until 4 choose 4, and then we'll do powers of each term. So for the one term, it would go from 0, 1, 2, 3, 4, and for the minus x term, we would get 4, 3, 2, 1, 0, the other way around. And if we just add all of these powers together, we would get, and this would be our expansion for 1 minus x to the power 4. And part B is asking to, using x is equal to 0.03 for the first three terms of increasing powers of x in the expansion, find the value of 0.97 to the power 4. Because if we substitute 1 minus x so that the x has 0.03 into before we expand it, we would get 0.97 to the power 4, which is what they want us to approximate. So if we substitute into increasing powers of x, we can just substitute and we'll get 1 minus 4, 0.03, because we're substituting x as 0.03 to approximate our expansion for this, plus 6, 0.03 squared is equal to, get 0.8854. Now for part C, they're asking to find the percentage error of this. Look at the formula, so we would have to find, we know what our approximation is, we know we need to find our actual value. So what we will do is 0.797 to the power 4, which is equal to, and if we substitute this into the equation, we're going to get, this was our approximation, and this was our actual value, which was our 0.97 to the power 4. And then we'll do this over our actual value, which is the 0.97 to the power 4, which is the same as this value over here. And we realize that the inside would be equal to minus 0.000121. It's because we have this function here, the modulus function, we can turn this into a positive. So this will actually be equal to 0.000121. And remember, because it's a percentage, we have to times this by 100. So we'll do 0.000121 times 100, which is equal to 0.0121%. And this is our value for our percentage error. So this is the end of the whole of binomial expansion. We've gone through everything that we need to know. Thanks for watching. I hope this was useful for you.